Here's the thing about the Google Cloud Professional Machine Learning Engineer exam. Google loves giving you 4 answers that all look reasonable, but only one is actually correct. And the difference? It usually comes down to one specific Google Cloud service or one keyword you might not have memorized. Vertex AI versus AI platform. BigQuery ML versus Stateflow. Integrated gradients versus Lime. Today, 10 real exam-style questions. And I promise question 5 is going to expose what most ML engineers don't know about Google Cloud. Let's go. Welcome to PrepMyCert. This is the Google Cloud Professional Machine Learning Engineer certification. 10 questions. 10 chances to prove you're ready. Let's go. Starting easy. Deep learning fundamentals. If you miss this one, the rest of the exam gets very hard. You're building a multi-class image classifier in Keras sequential. The output layer must produce probabilities between 0 and 1 that sum to 1 across the classes. Which activation belongs on that output layer? The answer is D, Softmax. This is the only activation that produces a normalized probability distribution. Every output between 0 and 1, all outputs sum to 1. That's exactly what categorical cross-entropy expects on the other side. Sigmoid is for binary classification or multi-label problems where each class is independent. Tan outputs negative values, so it can't represent probability. Real U belongs in hidden layers. It can return anything from 0 to infinity, which doesn't sum to 1 no matter how you scale it. Output activation has to match the loss. Multiclass plus categorical cross-entropy means Softmax every time. Next, picking the right metric. This trips people up because the obvious choice isn't the right one. You're evaluating a binary classifier on imbalanced data before you've picked a decision threshold. You want one metric that's both threshold invariant and scale invariant. Which one fits? The answer is an area under the ROC curve, or AUC. AUC is the only metric here that's both threshold invariant and scale invariant. It measures the probability that the model ranks a random positive higher than a random negative across every possible threshold at once. Precision, accuracy, and F1 all need a threshold first to count true and false positives, so they shift the moment you tune. And on imbalanced data, accuracy is dangerous. Predicting only the majority class can score 99% accuracy and tell you absolutely nothing about whether the model works. Now BigQuery ML. This one's pure SQL trivia, but it shows up on the exam. You're training a BigQuery ML linear regression on a wide view with many features and one label column. You want to feed every column except the label into the model without typing each name out. Which BigQuery clause does that? The answer is C, select star except label. This is standard BigQuery SQL, works in any query, not just BigQuery ML, and it's the clean way to feed a wide table into create model. The label gets its role assigned through the options clause with input _ label _ calls. The other 3 options don't exist in BigQuery. Select all but, select all excluding, and bare select excluding are all syntax errors. They sound right, which is why this question lands so often on the exam. Memorize the exact keyword except. Big infrastructure question. Your training job is taking days. What's the actual fix on Google Cloud? Your TensorFlow training job on Vertex AI is doing huge dense matrix multiplications, and a single epoch takes days on GPUs. You can't compress the model. The deadline is fixed. What gives the most aggressive speedup? The answer is B, switch to TPUs. Tensor processing units are Google's custom silicon, designed from the ground up for dense matrix multiplication inside TensorFlow. On large transformers and CNN workloads, TPUs are typically several times faster than equivalent GPU spend, and Vertex AI exposes them as a first-class accelerator. Pruning the model is off the table. You said it can't be simplified. Hand-optimizing GPU kernels is weeks of work and rarely beats just changing the chip. Distributing across more GPU nodes helps, but the per-chip throughput on TPUs eats that lead, and you spend less to get there. Alright, this is the one I promised. Vertex Explainable AI. Most ML engineers think they know the answer. Most ML engineers are wrong. You want feature attributions on your Vertex AI model for any prediction, which input features pushed it which way. You'll use Vertex Explainable AI's built-in methods. Which 3 methods does Vertex Explainable AI ship? The answer is a sampled Shapley, integrated gradients, and XRAI. These are the exact 3 methods Vertex Explainable AI ships. Sampled Shapley is for tabular models. Integrated gradients is for differentiable models on tabular or image data. XRAI is for image models specifically. It highlights the regions of the picture that drove the prediction. Knowing which method fits which model type is the real exam point. Lime and Full SHP are popular open-source libraries, but Vertex bundles its own implementations under different names. The other answer pairs mix interpretability with dimensionality reduction and visualization tools. They're not attribution at all. Production model is degrading and you don't know why. Classic MLOps incident. Which Google service do you reach for? Your ranking model on a Vertex AI endpoint suddenly performs worse. The model artifact and serving infrastructure are fine. Investigation shows one critical input feature has shifted distribution. Which Google Cloud service is purpose-built for this? The answer is C, Vertex AI Feature Store paired with Vertex AI Model Monitoring. This is the textbook feature distribution skew scenario. Production data no longer looks like training data. Feature Store gives you consistent feature serving with stored statistics. Model monitoring runs scheduled distribution comparisons against your training baseline and alerts when drift crosses a threshold. That's the named, managed combination for exactly this failure mode. BigQuery ML and Dateflow can compute feature statistics, but you'd build the alerting pipeline yourself. AI Platform Pipelines orchestrates training jobs. It doesn't watch live serving features. Algorithm selection question. Banks, signatures, forgery detection. What's the right model family? A bank wants to detect forged signatures on scan checks by comparing each new signature to the customer's stored reference image. Even skilled, visually similar forgeries must be flagged. Which model family fits? The answer is D, a convolutional neural network, typically a Siamese CNN. Signatures are images, and the signal is in subtle local strokes, pressure curves, loop shapes, pen lifts. CNNs are built for that. The Siamese setup specifically takes 2 images at once and outputs a similarity score, which is exactly the comparison task. Multiclass on raw pixels ignores spatial structure and won't scale across customers. Tabular anomaly detection means hand engineering features and losing everything CNNs find automatically. And logistic regression on pixel sums collapses an entire image into a single number. you've thrown away every bit of useful signal. High-dimensional features. Linear regression. How do you simplify without throwing signal away? You're training a Vertex AI linear regression on hundreds of correlated numerical features. You want to compress the input down to a few components while keeping as much variance as possible. Which technique fits? The answer is C, Principal Component Analysis, or PCA. PCA is the textbook move for dense, correlated, numerical features. It rotates the feature space and keeps the top axes that explain the most variance, so you can drop from hundreds of columns to a handful with minimal information loss. Feature scaling is pre-processing, not dimensionality reduction. Stepwise feature selection picks a subset of original features but ignores the correlations between the rejected ones, so it leaves variance on the table. K-means clusters rows, not columns. It groups similar examples, which doesn't reduce feature count at all. Quick framework question. PyTorch in a Vertex AI notebook. Save the model the right way. You're training a custom PyTorch model on Vertex AI and need to checkpoint it so you can resume later. Which call is PyTorch's recommended idiom? The answer is C, torch.save with model.state_dict. PyTorch's recommended pattern is to save the state dict, not the whole model object. The state dict is just a plain dictionary mapping layer names to tensors, portable, version resilient, and safe to load into a freshly constructed model with load_state_dict. Saving the whole model serializes the class definition, so any code refactor breaks the load. Model.save doesn't exist on nn.module, that's a Keras pattern leaking in. And torch.load reads from disk. Calling it on a state dict already in memory does nothing useful. Last one, cost. Your CIO wants the bill cut without sacrificing model quality. What does Google actually recommend? Training jobs are interruption tolerant. They checkpoint regularly and resume cleanly. You don't need predictable runtimes. The CIO wants to cut Vertex AI training spend. Which Google Cloud cost lever fits this pattern? The answer is a spot VMs, formerly called preemptible VMs, with checkpointing. This is the documented cost lever for fault-tolerant ML training. Spot VMs run at a steep discount versus on-demand, in exchange for the chance Google reclaims them with short notice. Vertex AI custom training supports them directly. As long as your job checkpoints to cloud storage every few minutes, a preemption is a non-event. The job just resumes from the last checkpoint. Reserved custom VMs cost more, not less. Hyperparameter tuning improves quality, but doesn't directly cut compute spend. And on-demand small instances are the most expensive way to train a serious model. That's all 10. How did you do? 8 or more. You're genuinely exam ready. The Professional ML Engineer Cert is one of the toughest in Google Cloud, and you just walked through the trickiest question patterns on it. 7 or below. That's exactly why you're here. The good news is you just saw 10 questions that look exactly like what Google will put in front of you on exam day. Drop your score in the comments. I want to see who's ready and who needs another round. If you want the full experience, hundreds of questions like these, detailed explanations for every one, and full practice tests covering every Google Cloud ML Engineer exam domain, head over to PrepMyCert.com. Lifetime access, one payment. And if you don't pass your exam, you get a full refund. No questions asked. The link is in the description. Go crush that exam.